Hey.
I'm here to start.
What?
I'm here to start.
And switch to Hebrew.
רק מסתכל עליך, נעשה לי קר.
דובר הוא תמיד ב5 מעלות יותר.
What?
You have to give people a few minutes.
Give people a few minutes?
So it's exactly 3:30. I mean, since when your soup is...
People were stopping, drifting in. Yeah, I think we'll start. People who are late, it's their problem. It's a great pleasure for me to welcome Erez Berg here. See, I had to start induce the influx. So it's an enormous pleasure for me personally to introduce today's colloquium speaker, Erez Berg. I'm, boasting when I tell you that he was my student here. But anyway, the current students can see that there is life after Stanford. So Erez actually got his master's with Asa Auerbach at Technion. Asa died a few months ago, and we're all somewhat in shock over this. Then he got his PhD here in 2009. He was a postdoc at Harvard until 2012, and he's mostly been on the faculty at the Weizmann Institute since then, with a brief sojourn on the faculty at the University of Chicago in between. Erez is well known for many creative and seminal contributions to many aspects of the theory of quantum materials, and ranging from being one of the leaders in the new field of 2D materials and twisted devices, through theory of interesting bulk materials and proposals of new ways of observing non-abelian anyons in mesoscopic devices. He's been recognized with multiple awards. I won't list them all, but I will mention there's an interesting online course called Topological Quantum Matter, which was posted by the Weizmann group. I recommend it to students who want to be introduced to this area. There are lectures there by many people on the faculty there, but the one that has the most hits is Erez's on topological phases of matter. So, all right, without further ado.
Yeah, okay, yeah. Thanks very much, Steve. It's always a real pleasure to be back here Feels like coming home, but this time it's a particular pleasure because of the happy occasion of celebrating the celebration we had last week of Steve's 70th birthday, and yeah, so right, I'm proud to be one of the chain of really wonderful students and postdocs, all educated here and in other institutions by Steve. So thank you very much for that as well. So I want to tell you a little bit about some things I've been thinking about that I started being obsessed by as a student here and also as a master's student already with Asa Auerbach. So it's a long-standing problem, and some of what I'm going to say are things that we've been thinking about relatively recently. So I'd particularly appreciate any feedback. Yeah, so I'll start by defining what I mean by saying strange metals. Okay, so it's an old topic with many different perspectives. I want to give you my particular perspective. Then I'll talk about metals close to quantum critical points as opposed to what I'll call critical phases or extended strange metal phases. And finally, I'll talk about a new model that we propose of how such a strange metal phase can occur from superconducting puddles. So this is a new theory. We are very convinced that the theory is true. Whether it has anything to do with what happens in real quantum materials, that's I think the jury is still out. But we believe it's an interesting theory. Yeah, so before starting to talk about strange metals, it's good to probably first talk a little bit about conventional metals. So one of the most successful theories we have in condensed matter physics is Fermi liquid theory of interacting fermions, and that theory can be applied across many metals. So this is, for instance, the Brillouin zone and the Fermi surface of copper. Okay, so this is the surface where the low energy excitations of the system are living. And remarkably, the consequences of this theory is that electrons, despite the fact that they interact with each other so strongly, can be described at low energies, energies much below the Fermi energy, very well by a model of independent electrons with modified parameters. So, for instance, the effective mass and the dispersion of these electrons would be very different from that of an electron in a vacuum. But that's all we need to know about the effect of electron-electron interactions. And otherwise, we can apply an independent electron model to describe many of the properties of the systems using just a few parameters that we can take from experiments. Okay, so this is a very deep and extremely successful theory in condensed matter physics. And what I'd like to describe are some situations where this theory fails. Okay, so this is an example of what this theory can give. So this is the electrical resistivity of copper as a function of temperature, and you see here different regimes, and all these different regimes can be described very well by basically Fermi liquid theory plus Boltzmann transport theory, fitting just a few parameters from experiments. So we understand well this very broad regime of temperatures where the resistivity grows linearly as a function of temperature. This is just a result of electron-phonon scattering. So the phonons are in the equipartition regime. The mean squared displacement of the ions of the metal is linear in temperature, and this is the reason why the resistivity grows linearly with temperature. And then below a certain temperature, the phonons freeze. The phonons become quantum. And there we have a crossover to a different regime where the resistivity is typically T to the 5th power from electron-phonon coupling, acoustic phonons. The prediction is that it should go like T squared ultimately at very low temperature from electron-electron scattering. Okay, and all these different regimes are very well understood, and we just need to fit a few parameters from experiment and really get all this behavior. Okay, so what is a strange metal? It's basically a metal where, which is outside of this framework of Fermi liquid theory plus Boltzmann theory down to the lowest measurable temperatures. Okay, so this would be my working definition of what's a strange metal. Okay, so now a common diagnostic of such a behavior would be the electrical resistivity, which is the easiest thing to measure, and that would typically go like some constant at low temperature plus some power in temperature. Okay, and Fermi liquid theory for a metal would predict that this power should be 2. So what we'll look for, what people find in certain systems, is power law behavior with a power which is less than 2. Okay, eerily often this power is 1. That means that the resistivity is linear as a function of temperature down to the lowest measurable temperature, but not always. I'll show you some systems where this deviation manifests itself in some other low temperature behavior, which is different than t squared. Okay, so here are some famous examples. This is a cuprate, a high temperature superconductor, and this is what happens when you suppress superconductivity by applying a magnetic field. So the resistivity continues down linearly down to the lowest measurable temperatures. There are other more recent examples. For instance, this is magic angle twisted bilayer graphene, where recently it's been reported that over a broad range of electron densities of fillings, the resistivity of this in the system is linear in temperature, and this extends down to a few tens of millikelvin, which is a very, very low temperature for this system. So why do we care about this behavior, about these strange metals? So I think there are basically two reasons. The first reason is that this is something that you can't find in our textbooks. So you can't find it in any solid state textbook. So there's something there for us to understand. The other reason is that this breakdown of Fermi liquid theory often comes together with some other interesting phenomena, like a superconductivity, for instance, unconventional superconductivity in particular, and as we'll see, quantum critical behavior. So it looks like there's something deep there to understand, which ties this strange metallic behavior to other interesting phenomena. Let me also mention, of course, the deviations from Fermi liquid theory go well beyond this behavior of the resistivity. This is just a common diagnostic of this behavior. This is often the first thing that you would see reported, but it often comes also with deviations from Fermi liquid theory that are seen, for instance, in specific heat, thermal transport, and so on. Okay, so in general, all the properties would be different from what you would expect in a conventional metal. Okay, so what's the source of this behavior? So first, I wanted to discuss a little bit what is causing the t squared behavior of the scattering rate in a Fermi liquid. Okay, so that's the conventional behavior. Where is that coming from? So the statement is the following: in a Fermi liquid, if we have a Fermi surface, and the low energy excitations of the system correspond to exciting a single particle or a single hole to an energy which is close to the Fermi surface, say some energy epsilon away from the Fermi energy. And the statement is, once we excite this extra particle, this particle is not an exact eigenstate of the system, so it would decay. Okay, and the rate in which it decays scales quadratically with the energy of that particle relative to the Fermi energy. So the scattering rate vanishes very rapidly as the energy goes to the Fermi energy. Okay, and that also means that if we're at equilibrium, we'll get a scattering rate, we'll get a relaxation rate typically, which scales like the square of the temperature, which is the typical energy of excited quasi-particles and quasi-holes. Okay, so where does this behavior come from? So that comes from a very simple phase space argument. So the argument is the following. Okay, so we start from some a quasi-particle, an energy epsilon away from the Fermi surface. How does that decay? That decays by electron-electron interactions, by colliding with other electrons from the Fermi sea. Okay, and so what's the phase space for this process? Well, we have to conserve energy. So this extra quasi-particle can lose some amount of energy by colliding with another particle. So there's some energy transferred delta epsilon that can be anywhere between 0 and minus epsilon. Okay, and to conserve energy, we have to excite a particle from the field Fermi C up to and give it the same amount of energy, delta epsilon. Okay, so we want to ask what's the phase space for this process. We have to integrate over delta epsilon from 0 to epsilon. We have to integrate over the initial energy of this excited particle from this Fermi C. You can see that that's independent. We integrate over that as well. So that gives us basically another factor of epsilon. So this is where the epsilon squared is coming from. Okay, very, very simple phase space considerations. Okay, now we ask, well, where would deviations from this behavior come from? For instance, where would a linear in epsilon and linear in t scattering rate come from? Okay, and this gives us a hint. Well, to get a scattering rate, which is parametrically larger than what we will get in a Fermi liquid, we must have some pileup of low energy states that would provide this anomalously large scattering rate at low energies. Okay, and this is really the key of the matter. We have to identify what's the source of this high density of low energy states in the system that are providing the extra scattering. Okay, and these extra states don't have to be anything very exotic. Okay, so here's an example for a relatively mundane way to get a deviation from Fermi liquid theory down to low temperatures. Okay, so suppose that we tune our system somehow into a saddle point in the electronic dispersion. Okay, so what's a saddle point? So this is the Brillouin zone. And there are some special values of some parameters, say the electron density. I'll show how to do it in experiment in the next slide, where so this is an example of a 2D metal. And what happens here is that the Fermi surface changes its topology from electron-like to hole-like. So basically, the Fermi surface reconnects with itself here and undergoes this topological transition. So close to this point, the electronic dispersion looks like a saddle. Okay, so it's a saddle point in the energy momentum relation of the electrons. And close to that point, in two spatial dimensions, it turns out that the density of states actually diverges logarithmically. So what we'll find here, okay, so suppose that our Fermi energy somehow can be tuned to be very close to this log divergence in the density of states. Okay, so then we'll have a lot more phase space to scatter electrons. So in particular, okay, suppose that we start from an electron somewhere here. This is our excited electron. It can scatter into that state. And to conserve energy and momentum, we scatter an electron from the field Fermi C to the Van Hove point. But there's sort of a lot of ways we can do this because there's so many states close to this sort of hotspot. Okay, so if you do the calculation, it turns out that the resistivity, the electrical resistivity, actually in this kind of situation goes like t squared times log of 1 over t times with some energy numerator. Okay, so now this is a little bit counterintuitive because all the pileup of low energy density of states is happening at one point or a few isolated points in momentum space. So it looks like transport would not be sensitive to these isolated points. The electrical current is carried by the entire Fermi C, not just by the parts of the Fermi C that are close to these Van Hove points. But it turns out that the possibility to scatter electrons into these points with a very high density of states can actually affect the relaxation rate of the current over the entire Fermi C. Okay, and this is where this behavior is actually coming from. Now, the interesting thing, yes, yeah.
Is this an umklapp?
This particular process I drew here is an umklapp, yeah. Yes. Yeah, so this electron is really scattering to the other Brillouin zone. and then I have to backfold. Yes. Yeah, so so this, thinking about this was actually triggered by an experiment. So it turns out that in certain systems, you can really do this. You can really tune your Fermi sea to be at the Van Hove point. So this is actually how it's done. It was first done in this material strontium ruthenate, which is actually a very interesting material for various reasons. But Cliff Hicks, who's a Stanford alumnus, did this beautiful experiment where it's a tetragonal system, meaning that the crystal has a square symmetry. And by applying strain, you can modify the electronic dispersion of the different bands in this system. And it turns out that at zero strain, there's a particular band called the gamma band here, which is naturally very close to the boundary of the Brillouin zone. So it doesn't take a lot of compression or tension to actually bring the Fermi surface to the zone edge where it meets its Bragg reflection and undergoes this Van Hove singularity. So this is the calculated electronic structure in the system. And it turns out that this calculation actually captures correctly where the system would cross the Van Hove singularity. Okay, so there's actually been recently there's been a beautiful photo emission experiment which actually images the band structure as a function of strain. And you can really see how this saddle point topological transition in the Fermi surface is occurring at the edge of the Brillouin zone. Okay, so this allows you to actually measure in what strain corresponds to the Van Hove singularity in the system. And what Cliff did back in 2018 is to measure the electrical resistivity as a function of temperature and strain, showing this kind of phase diagram. So this axis is compressive strain, and this axis is temperature. And what's actually plotted is the log derivative of the resistivity where you subtract the zero temperature extrapolation of the resistivity. Okay, so this gives you, if you like, the exponent, the local exponent with which the resistivity is varying as a function of temperature. Okay, and what you should see here roughly is that it's bluish on this side, bluish on that side. That corresponds to an exponent of 2. This is what you would expect in a Fermi liquid. But close to this special value of strain, you see this kind of fan-shaped region where the exponent seems to deviate significantly from 2. It's below 2. This is a behavior that you would usually associate with some kind of quantum critical point. Okay, so you would imagine that at zero temperature, there's some critical point that you can't quite reach, but you can try to approach from higher temperatures. And the behavior of this quantum critical point would manifest itself in anomalous scaling that would extend in this fan-shaped region in this case in the strain and temperature plane. Okay, but here the quantum critical point is actually very simple. It's just this topological transition of the Fermi surface. This is all what's going on here. Okay, and moreover, it's been measured. This is just the resistivity as a function of temperature at the critical strain, and you can fit it to a power law. If you try to do that, the power is close to 1.5, but it fits equally well to this form of t squared times log of 1 over t. And it turns out there were later experiments by Cliff where he so it turns out that you cannot actually extend this measurement below 3 or 4 Kelvin because the system goes superconducting at that point, so you cannot measure resistivity anymore. In fact, superconductivity is extremely strongly enhanced exactly at this point, exactly when you tune the system to the vicinity of the Van Hove singularity. But Cliff has since done experiments where he suppressed superconductivity by applying a magnetic field, and he claims that the t squared log t actually fits the data better when you go to lower temperature. So this is, if you like, sort of a trivial example of a strange metal behavior, not of the most exotic type. It's not the strongest deviation from t squared. It's just t squared log t that you can really understand almost quantitatively. Okay, and there's really nothing exotic going on. You just need to understand where this extra pileup of low energy states is coming from.
So 3 halves
It's an illusion.
The 3/2, if this is true, the 3/2 is a delusion here, yeah. So following up on the same logic with Sean Hartnell when he was here and a student, Connie, we tried to think, well, suppose we can design some density of states and whatever density of states that we want, what profile of density of states as a function of energy would actually produce a linear in T resistivity. There is a simple density of states that would do that. Basically, if you have a coexistence of itinerant electrons for being a dispersive Fermi sea and a flat band, okay, so you have a constant density of states plus a delta function, and you tune that delta function to be exactly at the Fermi energy, that by the same phase space argument, that actually produces a linear in T resistivity. Okay, and we even tried to argue that the behavior of a different material that I'll show in a slide or two can maybe explained by this simple model. Now, this has some problems with it. Okay, flat bands are very non-generic. That's a very unstable situation in many respects. Unlike the previous case of a saddle point, which is sort of generic, you only need to tune one parameter, as we saw, to reach a saddle point. Here you have to tune much more. Okay, so and even if you could somehow tune the system to be in this flat band regime, there are good reasons to think that this cannot extend down all the way down to the lowest temperature. The system would just develop some other instability and avoid this point. Okay, nevertheless, it's sort of an interesting question. For instance, just one sentence. In Twisted by Larry-Goffin, we believe now that this kind of situation of coexisting itinerant electrons in very flat bands may exist in some regime of the phase diagram. Yeah.
I mean, this is quite generic in heavy fermion systems, right?
Yeah. So right. So this is quite generic in heavy fermion systems. However, if you think about heavy fermion systems, with this requires you to tunnel into the F electrons. So you better be sort of one of the Hubbard bands needs to be at the Fermi energy.
Okay.
Yeah, but otherwise, yes. Yeah. All right. So so I'd like to talk a little bit about quantum criticality, quantum critical points, and what I'll refer to as quantum critical phases. So if you think about strange metal behavior, there's a very natural route to achieve that. Okay, so what we want to do is to destabilize the Fermi liquid somehow by creating this anomalously large low energy density of states. And there's a very natural way to do that, which is to tune a Fermi liquid to a quantum critical point. Okay, so to tune the system exactly to the point where the Fermi liquid is on the verge of becoming unstable to developing some other kind of order, and then the quantum critical fluctuations of that order would provide the low energy states that can destabilize the Fermi liquid. And that seems to happen in nature in many examples. Okay, so this is a different ruthenate material. This is an old experiment by Andy Mackenzie's group. Okay, and here it's a beautiful Fermi liquid at zero magnetic field, but as you apply a magnetic field, it looks like you're tuning the system to this quantum critical point. Here's a heavy fermion example. Okay, so again, similar behavior. So a T squared resistivity on both sides of some critical magnetic field. Here we actually know what is going on at this critical point. Okay, so this side of the phase diagram is magnetically ordered, and this side is not. So presumably we're just destroying the magnetic order by applying a magnetic field. Okay, so and there are many examples of materials that seem to follow this kind of paradigm, that there is strange metallic behavior that seems to be confined to a quantum critical point at zero temperature and then extends at finite temperature to this fan-shaped regime. However, unfortunately, I think we don't have a good theory that would relate the quantum criticality to this anomalous scattering rate. So this has been an open problem for a very long time, and I think there are many ideas, but there's no accepted theory, at least, to produce this behavior. There's some recent ideas that maybe having spatial inhomogeneity is important in order to get the scattering rate even in the vicinity of a quantum critical point. So this, despite its apparent appeal and simplicity, this is actually an open problem. However, that's not what I'm going to talk about in the rest of this talk. How much time do I have, by the way? Okay, yeah. So I can go slowly. So yeah. So what I'm going to talk about is a different phenomenon. So this is a similar plot as before for a Hove-doped cuprate. Okay, so this is a Hove-doped cuprate. It's a high temperature superconductor, and again, what's plotted here is a phase diagram. This axis is doping, so basically the number of carriers doped into the system, and this is temperature. And what's plotted is, again, is the exponent of the resistivity as a function of temperature. It's basically the log derivative of the resistivity with respect to temperature. Okay, so at zero magnetic field, the system is actually a superconductor. This dashed white line here is the superconducting TC. So below this amount of doping, we actually can't measure the resistivity at low temperature. But what's been done in this experiment is they applied a huge magnetic field that suppresses TC sufficiently such that you can actually measure the resistivity as a function of temperature even inside what would be the superconducting phase at zero field. Okay, so if you like, they want to say, let's suppress superconductivity completely and reveal what the metallic state, which is the parent state of the superconductor, would have been like if superconductivity was somehow forbidden. Okay, and what you see again is this color plot, the exponent of the resistivity, where 2 is what we would expect for a Fermi liquid. And you see this very strong deviation from 2. It's actually close to 1, close to linear in T resistivity. This is the famous linear in T resistivity in cuprates. But unlike the cases shown before, this behavior is not confined to a quantum critical point. It actually extends over a whole regime of doping. Okay, so there's a whole, if you like, a whole phase, apparently, which is characterized, a whole metallic phase, which is characterized by rho being proportional to T. And moreover, this region where the resistivity is linear in temperature seems to terminate not too far from where superconductivity terminates. Okay, so these are the two observations. I'll be focusing on this type of regime. In the jargon of the field, this is called a foot, okay, for obvious reasons. So there seems to be, if you like, a strange metallic phase or a quantum critical phase rather than a quantum critical point. And this is, if we don't have a good theory for quantum critical points, this is much worse. And there is this apparent correlation between the end of the superconducting dome and the end of this strange metallic regime, where it starts to cross over towards 2, the T squared, which is what we would expect in a Fermi liquid. Okay, now, interestingly, this phenomenology is actually not special to that cuprate. Okay, it's observed in other cuprate materials, and it's even observed in other unconventional superconductors that chemically have nothing to do with the cuprates. They're extremely different. So this is an organic superconductor, which is tuned not by doping but by pressure. So here there's actually a spin density wave or a antiferromagnetic phase, which is suppressed by applying pressure. And then there's an unconventional superconductor, which is suppressed at a critical pressure. And in all these systems, it looks like you can fit, so the empirical observation is that you can fit the resistivity as a function of temperature to this simple form of linear in T. So basically some coefficient A times T plus B times T squared. And the observation in this article is that in both of these systems, the coefficient of the T squared term is more or less tuning parameter independent or weakly dependent on either doping or pressure. But the coefficient of the linear in T term seems to vanish. So it's decreasing as you approach the end of the superconducting phase, of what would be the superconducting phase at 0 temperature or 0 field. Okay, and it's vanishing. So here, the claim was that it's vanishing very close to the end of the superconducting regime. Here, in this paper, the two are a little bit separated, but still, it looks like they're close. Okay, so this is basically what I'll be trying to explain in the remainder of this talk. Okay, and this is work that we've been doing over the last year. I was fortunate to work with some great people. So Jörg Schmalian from Karlsruhe, this project really took off when Jörg visited our group for a few months last year. My two great students, Noga and Eviatar. Eviatar is actually graduating this year and joining here as a postdoc, and Steve, who you all know. Okay, so how do we understand this sort of behavior? Okay, so we have strange metal behavior that seems to be tied somehow to unconventional superconductivity. The two seem to terminate at the same point. They're correlated, and also they're quantitatively correlated. Where Tc is high, the coefficient of the linear in T scattering is also large. Okay, so if you like, there are two logical ways to approach this. The first one is that there's something that's causing the superconducting pairing of electrons, and the same thing is also causing the scattering. Okay, and this point of view was actually taken by this recent series of works by Subir Sachdev and collaborators. The idea here was that there's actually some kind of quantum critical point here that so the particular type that was discussed in these works was an antiferromagnetic quantum critical point. And if our system was perfectly homogeneous, then we would see the familiar fan-shaped strange metallic behavior terminating at this point, and this would be a Fermi liquid. However, because of disorder, because of inhomogeneity, there's what's called the Griffiths phenomena. Some regions of the sample actually look like they're already in the ordered phase, already on this side. Okay, so there's this plethora of low energy spin fluctuations that are causing the strange metallic scattering over this entire regime. And it's actually the same spin fluctuations that would also cause the pairing, and hence the correlation between strange metallic behavior and superconductivity. We actually pursued a different approach. So we want to say, well, what if it's actually the remnants of superconductivity that exist even when global superconducting phase coherence has been suppressed, either by applying a high magnetic field or by raising temperature. Suppose that we, once again, the system is microscopically inhomogeneous. So we suppress global superconductivity. The system globally is a metal, but there are some remnants, local remnants of superconductivity that remain throughout this entire regime. And what if it's these remnants of superconductivity that are causing the scattering, which is giving rise to this linear in T resistivity? Okay, so what are these remnants? Well, they're good experimental evidence that in the overdoped cuprates throughout this regime, throughout this doping regime, even when you suppress superconductivity, for instance, if you just heat up the sample above DC, superconductivity is actually not destroyed everywhere. Okay, and there are a lot of different pieces of evidence from experiments that are leading to this. Okay, the most direct one is STM. So by doing scanning tunneling microscopy, you can measure the local gap, the local gap in the electronic spectrum that you can associate with superconductivity. And these are older experiments by Elias Dani. There were also experiments done here by Aaron. And these are some more recent experiments by Milan Allen's group. Okay, and for instance, in these experiments, green means gapped. So the green color means that the electronic spectrum, so basically there's a scanning tip that measures tunneling spectroscopy at every spatial point. And in these green regions, you see a gap. There's a suppression of the electronic spectrum at low energies. This is what happens at low temperature below TC, and this is actually above TC. So much of the sample is actually still gapped. So there's the white regions that look metallic, but locally in some regions, the spectrum still looks like the spectrum of a superconductor. Okay, and what's causing this behavior? So I think we have some understanding. Okay, so let me also mention that there are other pieces of evidence from other kinds of experiments that can be explained by this picture of an inhomogeneous superconductor, where they're basically little patches of superconductivity living inside a metallic environment.
What is the temperature above TC for the last sample?
Yeah, so what's the temperature here? I don't remember. Here it's, yeah, I mean, this is a 60-odd Kelvin superconductor.
Yeah. Excuse me, this is, I'm a little lost. This is not, is there a magnetic field in the picture?
Not here, no.
So this has nothing whatsoever to do with the foot?
Well, yeah, so.
Nothing whatsoever. With the what? With the foot.
Yeah.
The foot is unmeasurable unless you crush the superconductivity.
Yes, yeah. So.
This is not a theory of the foot, this is a theory of something else.
Yeah, so.
What is the theory of?
Yeah, so so far there has been no theory. This is, yeah, so this is just an observation. Now, yeah, what I'm going to say soon, as you guessed, is that for the same reason that some of these superconducting patches survive at high temperature, they also survive in a magnetic field. There's no direct measurement of that at the moment. This is one thing that we want people to try to measure. Yeah, so yeah, let me say that.
Is it completely clear that's a superconducting gap and not a different kind of gap?
Yeah, definitely not from this type of experiment. Yeah. Yeah, right. Okay, so what's actually causing this this type of behavior, this sort of inhomogeneous suppression of superconductivity? So we think we have some understanding thanks to work done by Steve. So this has to do with the way that superconductors react to disorder. Okay, so we understand that if we have a conventional S-wave superconductor that's relatively insensitive to disorder, but an unconventional superconductor like these cuprate materials are, like a D-wave superconductor, is actually extremely sensitive to disorder. And that means that when you add disorder, it would be destroyed eventually. But because of the random distribution of impurities, it won't be destroyed at the same temperature or field at the same time. Okay, so this is a picture from a simulation, basically of a BCS mean field theory of a disordered S-wave versus D-wave superconductor. And this is just a picture of the local superconducting order parameter. And you see that it develops kind of spontaneously these structures in the D-wave case. Okay, so what we're going to propose, indeed, is that even when you apply these large magnetic fields in the foot to suppress superconductivity, superconductivity is actually not destroyed everywhere. Okay, so there are these little patches. We're guessing that these patches are just a few nanometers across. Okay, so we're imagining this kind of situation where we have a metallic environment and we have these little superconducting puddles that survive, and then these puddles would scatter incoming electrons. This is actually an Andreev scattering. So an incoming electron can get scattered can get reflected as a whole, and we want to study the possibility that this is actually the source of this anomalous low energy scattering rate that's giving rise to the foot. Now, an important comment here. Okay, so if we have these superconducting puddles they can also Josephson couple to each other. So in addition to scattering the electrons from the metal, these puddles can actually carry a supercurrent just by locking their phases together. We're imagining that we're far enough from the critical field, and as we'll see, the superconducting phases of these puddles are quantum fluctuating enough that we can actually neglect the Josephson coupling between these puddles. Okay, so we'll actually treat the model that I'll sketch is actually treating a single superconducting puddle coupled to a metallic environment, and I'll study the scattering rate, the Andreev scattering rate of electrons off this puddle. And I'll basically imagine that all the other puddles are far away enough that they don't interact.
So you assume that there is Andreev scattering and some abnormal scattering?
Yes, yes.
Doesn't...
Yes, yeah, yeah. All right, so yeah, so of course I won't go into a lot of details. I'll just try to sketch how we model the system. Okay, so it's sort of a nice exercise in model building and condensed matter. So we just start from a single isolated island like this, and we imagine that the important degree of freedom is just the charge, just the number of Cooper pairs that are living on this superconducting island. And suppose that we first somehow turn off the tunneling of electrons in and out of this puddle, then this puddle has some charge, okay, characterized by n, which is the number of Cooper pairs, and it has some preferred charge, n bar. Okay, so n is an operator which has integer eigenvalues, so it's an integer. N bar does not have to be an integer, and n bar is somehow a function of the local electrostatic environment, if you like, of this puddle. So that's a continuous variable, and the energy spectrum of this puddle would look like this: just discrete integer n's have a parabolic energy as a function of n, and there's something special that happens. So this n bar we'll treat as a random variable. There's something special that would happen when this n bar is exactly half. In that case, the two lowest energy levels in the system would be degenerate, basically n and n plus 1 number of Cooper pairs. And if we tune it a little bit away from half, then we'll lift this degeneracy. Okay, so we'll treat this n bar as a random variable, which is uniformly distributed. There's no particular reason why a particular puddle would favor a particular value of n. Okay, so now we'll consider the coupling of this island to electrons. And indeed, electrons can either Andreev reflect off this island, or they can also do normal reflection, meaning that an incoming electron is reflected as an electron. Okay, and we describe this coupling in terms of the simple Hamiltonian. Okay, the geometry of this island is all encoded in this function g of k and k prime. Basically, that's the scattering amplitude of an incoming electron with some momentum in an outgoing hole, in this case, with some other momentum. Okay, I didn't write it here, but there's also a normal reflection that turns out to be less important when you analyze this problem. Okay, but it's also there in our modeling. It's convenient to characterize this by a single number. Okay, so in principle, there's a whole coupling function here, but there's a dimensionless number which is useful, this dimensionless coupling in the Andreev channel alpha perp. Okay, so that's the coupling strength. Okay, now in principle, we have this entire tower of excited levels of this island, but if we're at energies that are far enough below this charging energy U naught, then we can focus only on the two lowest energy levels, especially for superconducting islands that are close to this degeneracy point of n bar equals half. So there are only two levels that are close by, and all the other levels are far away. Okay, so what we can do is reduce the problem to that of a two-level system, only two states, with n Cooper pairs and n plus 1, that are interacting with the metallic environment. Okay, so there's just a pseudo-spin sigma. Sigma z up means n plus 1 Cooper pairs. Sigma z minus means n Cooper pairs. Okay, and that's coupled to the electrons in this way. So this is a model of a two-level system interacting with electrons. In other words, this is actually a very familiar problem in condensed matter physics. This looks almost like the so-called Kondo problem of a spin, of an actual localized spin, which is interacting with a metal. Okay, but the difference is that it's not a spin, it's a pseudo-spin. The two levels are not up and down, they're n and n+1 Cooper pairs. And it turns out that that can also create a Kondo effect. There's something called the charge Kondo effect, which is exactly a realization of this type of Hamiltonian. It's a very different system, but it's been discovered here by Ian some years ago. Okay, so this is actually the problem that we'll study. It's a multi-channel charge Kondo effect, a charge Kondo problem with a number of fermionic channels, incoming and outgoing channels, interacting with this a charge Kondo impurity that scales like a kf, the Fermi momentum, times the r, which is basically the size of the perimeter of this superconducting island. Okay, so this number, if we think that the size of these puddles is maybe a few nanometers, this number is maybe 10 or 20. So that's the regime we'll be interested in. Okay, and yeah, so I won't go into a lot of details. I'll just flash a few results coming from analyzing this model and conclude. Okay, so let me first give a cartoon picture of why this kind of model might give you linear in T resistivity. Okay, really at the very simple-minded way. Okay, so the reason is very simple. If you think about the density of states of these two-level systems, these charged two-level systems with n and n+1 Cooper pairs, let's assume that the offset charge is uniformly distributed, so they have a constant density of states. And if you think about Andreev scattering in particular, you have an incoming electron with some energy epsilon above the Fermi energy that can scatter, undergo inelastic Andreev scattering. So it can scatter to a hole, basically at any energy from epsilon down to the Fermi energy. Okay, and there's a constant density of states that can account for energy conservation in this scattering process. Okay, so the phase space for this process is just linear in epsilon. So that kind of naturally gives you a linear in energy scattering rate. And by the same token, it would give you a linear in temperature scattering rate for the current. Okay, so that's very simple. And of course, the devil's in the details. You have to do the full analysis. So one question that we wanted to address is what is actually special about superconducting puddles as opposed to some other impurity, like a charge impurity or a spin impurity? So if you try to replace the superconducting puddles by some other source by some other localized degree of freedom that can scatter electrons, can the same mechanism work? And it turns out that no, there's something very special about these superconducting puddles. There's a U1 symmetry in the problem, which just corresponds to the charge conservation in this Andreev process. And if you try to solve a similar problem of localized two-level systems interacting with electrons, you find that there is a strange metal phase, if you like, or a strange metal regime, but the scattering rate doesn't necessarily grow linearly with temperature. It's actually there's an exponent of the resistivity as a function of temperature, but that exponent is actually varying continuously as a function of microscopic parameters. Now, the second question is, from this heuristic argument, we argue that we get T-linear behavior or epsilon linear behavior. Can that actually survive all the way down to zero temperature or zero energy? So is the system actually the ground state? Is this state actually the ground state of the system, or does it become unstable to something? Okay, and it turns out that ultimately this linear in T behavior does not extend all the way down to zero temperature. There is Kondo screening. So this is a phenomenon well known from the Kondo effect. If you have a spin impurity in a metal, and it's antiferromagnetically coupled to the spins of the surrounding electrons, at low energy, it tends to form a singlet with the surrounding, with the spins of the electrons from the Fermi C, and it basically disappears from the low energy theory. And this actually happens here as well. The charge Kondo effect can also undergo Kondo screening. It just turns out that in this problem, the effective Kondo temperature where this occurs is exponentially small in this parameter KFR, basically with the number of electronic channels that are trying to screen this impurity. Okay, so this is something we rediscovered. It turns out this was a phenomenon that was known in the literature. If you have many channels trying to screen the same spin, if you tune them all to be exactly the same coupling strength, they would never be able to screen. They just compete all the way down to 0 temperature. If you make the couplings a little bit, you consider some distribution of coupling constants, then you do screen eventually. One channel wins, but that happens only at exponentially low energy scales in the number of channels. Okay, and this is an RG calculation with some distribution of coupling constants with a varying number of channels. So this is what happens to the dimensionless coupling constant as a function of the running RG time. And it's beginning by flowing down, okay, undergoes a minimum, and eventually there's one channel that wins and takes it all, okay, and just screens the impurity. So this is RG time, so there's an exponentially energy window where this simple-minded picture that I showed before actually works. So this is the phase diagram that we would expect that we derive for this model. Okay, at very high energies, there's a non-universal regime down to the renormalized charging energy of the typical charging energy of the superconducting puddle. Then we have this energy window between the charging energy and the Kondo temperature, the charge Kondo temperature, where the resistivity is linear. This is actually a marginal Fermi liquid. So the resistivity is linear. We also predict that the specific heat should have this log T anomaly with a coefficient that depends continuously on doping. And ultimately, at the very lowest temperatures, we get the charge Kondo effect and we recover from Fermi liquid theory. Okay, so yeah, so that's basically what I wanted to say. So let me conclude. Okay, so this is applying the Anna Karenina principle to strange metals. So the more we think about it, we believe that there isn't one universal mechanism for strange metal behavior, even though they may look similar, but there could be different origins. And I've shown you some particular scenarios, some of which we think we understand, some of which are more speculative. Let me mention some open problems. Okay, so this picture of small superconducting inclusions in a metal may work to explain the foot region, the overdoped region, the cuprates, but it kind of hides the elephant in the room. There's the fan. There's the linear in T resistivity that extends down up to very high temperature, close to optimal doping. That theory definitely is not the right theory for that behavior. We have to assume that these two behaviors have a different origin. We say nothing here about so-called Planckian dissipation in many of these systems where the resistivity is linear in temperature. It looks like the scattering rate actually scales with temperature in this very simple form with a coefficient which is a 4-to-1. We have nothing to say about that. We actually think mostly we approach the problem from the regime where this coefficient is much smaller than 1. And we have to extrapolate to get 1. Okay, so yeah, with that, let me conclude. Thank you very much.
Yeah, I had a question about the phase diagram of the exponent of the resistivity with respect to temperature from the Hussey paper.